To derive the Snell's law, that is mu1 sin I equal to mu2 sin R, we have drawn a figure in which the rays are the incident ray falling at an angle of incidence I, and the refracted ray comes out with the angle of refraction R. First media has the refractive index mu1 and velocity v1, and second media has the refractive index mu2 and velocity of light in second media is v2. AC is the incident wavefront. The point A of the incident wavefront meet at the boundary of the two media. So other point of the wavefront, that is the C, which reaches at B after the time t. So in time t, this wavefront travels the distance equal to v1 into t, because v1 is the speed of light in media 1. Similarly, in same time, the refracted wavefront, which is BD, this is the refracted wavefront, whose point A travels to point D in time t, and this distance is v to t. Angle of incidence is I. Therefore, the wavefront makes angle I with the boundary. We can see it by the geometry. Similarly, refracted wavefront makes the angle R with the boundary. So we can find sin I by sin R. This is the ratio of the incidence angle and sine of refracted angle, that is equal to, from geometry we can see that in triangle ACB, sin I is equal to perpendicular oblique hypotenuse, that is BC by AB, and BC is V1T. So it is V1T by AB. Similarly, in triangle ADB, sin R, that is the angle of refraction, this will be perpendicular, that is AD divided by AB, and AD is V2T divided by AB. So we substitute value here, V1T by AB divided by V2T by AB. This AB and AB get cancelled, and T also get cancelled. So remaining is V1 by V2. We have discussed that refractive index in a media is C by V, where C is the speed of light in the air and V is the speed of light in media. So V equal to C by mu. Therefore, V1 can be written as C by mu1 and V2 can be written as C by mu2. C and C get cancelled, so it is mu2 by mu1. And we can also write it as mu21 or mu. This is the called refractive index of medium 2 with respect to medium 1. So from the equation we can finally calculate that sin I by sin R is equal to mu2 by mu1, or cross multiplying we will have sin I mu1 into sin I equal to mu2 into sin R. Case of normal incidence, that is when the incident light fall normally along the normal. So in this case, angle of incidence is 0 degree. Therefore, this implies the angle of refraction R will also 0. That means the ray moves in the along the same direction. This is the incident ray and this is the refracted ray. Same can be verified from the Snell's law, that is mu1 into sin I equal to mu2 into sin R. Here I is 0 degree, so mu1 into sin 0 degree equal to mu2 into sin R. Sin 0 is 0, so it can be written as sin R equal to 0 or R equal to 0 degree. So angle of refraction is 0. Next is critical angle and total internal reflection. Suppose we consider two media separated by the boundary, and a ray incident at an angle of incidence I. And first media is the denser media and second media is rarer media. That means mu1 is greater than mu2. In that case, ray deviates away from the normal. And angle between the refracted ray and the normal is the angle of refraction. This is the first case. In second case, if ray incident at a particular angle I, that is say IC, we say it is a critical angle, at the boundary of two media 1 and 2, where having the refractive index mu1 and mu2, with mu1 is greater than mu2. That means ray is moving from denser to rarer medium. Again, it will deviate away from the normal, and in this particular angle of incidence IC have the angle of refraction of 90 degree. This is the second case. In this case, when angle of refraction is 90 degree, the angle of incidence is IC called critical angle. And in third case, with the same media 1 and 2 with refractive index of 1 greater than of 2, ray incident at an angle of incidence I greater than IC. That is, now angle of incidence is greater than the critical angle. In that case, no refraction take place and ray return back into the same media. It means it has the angle of reflection R and there is no refraction. This is called the case of total internal reflection, or in short TIR. So we can say that when ray propagate from denser to rarer medium for 90 degree of angle of refraction, second case here, then corresponding angle of incidence, which we have shown by IC, is called critical angle. And when incidence angle is greater than IC, no refraction takes place, called total internal reflection, in short TIR. It is to be noted that critical angle IC does not depends on angle of incidence. Rather, it depends on refractive index of medium. So, for critical angle, we can write refractive index of 2, that is the rarer medium, divided by refractive index of first, that is the denser medium. It is equal to sine IC by sine 90 degree, or it is equal to sine IC. If first medium have the refractive index mu and second medium is air, that is its refractive index of is 1, so we can write that 1 by mu equal to sine IC, or sine IC equal to 1 by